So nuclear power is basically looking at nuclear reactors for the generation of electricity. Worldwide in 2007, I know that's a little dated, but in 2007 there were 439 nuclear power plants in the world, with a generating capacity of 384,000 or 384 gigawatts, 384,000 megawatts. That was the amount that was in commercial production. A general rule of thumb is that the fission of 1 gram of uranium produces the energy equivalent of 10 tons of oil. The fundamental idea behind a nuclear reactor is to provide radioactive fuel in an environment such that nuclear reactions can proceed in a safe and dependable manner to provide power to generate electricity. For that to occur, a sufficient quantity of neutrons must be produced to sustain a controlled nuclear reaction, sufficient to provide power. Uranium, for example, is a common fuel for many reactors and will fission in many different ways, resulting in various fission products. A general nuclear reaction for a large cohort of atoms will result in what we call the average reaction, according to a publication by Murray in 1961. So we have uranium-235, and a neutron will yield uranium-236 and what we would call fission fragments, along with approximately 2.43 neutrons. Fission fragments are, again, what is resulting in the product side of the reaction. The mass numbers of those fission fragments and the neutrons must sum to 236. On average, in that case, 2.43 neutrons are produced. If the reaction is to be sustained, then at least one of those 2.43 neutrons must be absorbed and result in the fission of the nucleus of another uranium-235 atom. So let's look, for example, at this case. We have, the question is asking how much uranium-235 is required to produce 1 megawatt day if the average energy yield is 200 mega electron volts per fission and the electrical conversion efficiency is 35%. So let's look, for example, at what 1 megawatt is. 1 megawatt is, of course, 1 million watts. So 1 million watts is 1 million joules per second. And if we continue our conversion, we get that 1 mega electron volt is equal to 1.6 times 10 to the minus 13 joules. And then in the case of this example problem, it's saying that 1 fission is equal to about 200 mega electron volts. So in that case, we would know that in the case of this reaction, that 1 megawatt has to equal 3.121 times 10 to the 6th fissions per second. And in the case of uranium-235, we know that the mass of an atom can be computed, since 235 grams of uranium-235 contains 6.023 times 10 to the 23 atoms per gram mole. So if we do the math, we get that we have 3.9 times 10 to the minus 22 grams per atom. So if we were to look at 1 megawatt day, we will take our 3.121 times 10 to the 6 fissions per second. Look at the amount in a day. We have 86,400 seconds in a day. That again multiplied by 3.9 times 10 to the minus 2 grams per atom, where we would need 1 atom per fission. Once we do that math, we would get that for 1 megawatt day, we would need 1.052 grams of uranium-235 per day. And if we take into account a 35% efficiency, we would basically take that 1.052 grams per day and divide it by our 35%. And we get that we need approximately 3 grams per day of uranium-235 to get 1 megawatt.